It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with Helen Scales. Hi, Helen.
Hello.
Dave Ansell.
Hi there.
And I'm Chris Smith. Now, this week, researchers have discovered the world's loudest land-living animal. It's louder even than a Meatloaf concert, and that should give you some clues as to what it is. Also, monsters from the deep. We've got an update for you on giant squid. And is this the basis of bird navigation? Scientists have found a chemical trick that might enable birds to see the Earth's magnetic field. And we'll be hearing how it works very shortly. Helen.
Thanks, Chris. This week it's also our science question and answer show. So we'll be tackling your science questions, including finding why Matthew's ice cubes are vanishing from his freezer, why your stomach gets left behind whenever a car goes over a bump. Plus, in this week's question of the week, we'll be shedding some light, and that's torchlight, on the hot topic of how to keep the Olympic torch alight in mid-air.
I was wondering how you transport a naked flame on an aeroplane. It has to be a naked flame, I think, to continue the Olympic spirit. But it's obviously possible, so I wondered how they did it.
So, how do we keep that flame alive? Diana will be here with the answer to that later on in the programme. Dave?
Thanks, Helen. And in this week's Kitchen Science, I'll be showing you an example of rubber behaving badly. If you'd like to have a go, all you need is a large elastic band and your face. I'll tell you how to do it shortly.
That sounds painful. Thank you very much, Dave. So, if you've got a question for us on anything science, and the wackier the better, do get in touch. Email us, chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's take a look at some of this week's hottest science news stories from all around the world. This week's no exception, because scientists working in Panama, they're actually from Denmark though, have discovered that the loudest land-living animals on Earth are in fact bats. Would you believe it? Thank God we can't hear them, though. They're screeching, or maybe that should be roaring, at 140 decibels at times. This is a study done by Anne-Marie Serliker and Elizabeth Kalka. They published it in PLOS ONE this week. They went to Panama. They put some sensitive microphones in trees, and then they recorded from these microphones as the bats flew towards the microphone, and they were able to use the distance from the microphone the bats were at to work out how loud they must be, and also what the frequencies they were running at were. And what they found was that the bats produced sounds between 25 and 75 kilohertz. Now, to put that in perspective, our hearing cuts off at between 15 and 20 kilohertz, so this is far too high for us to hear. But the amplitude, how loud the sounds were, was really impressive. 125 to 140 decibels of sound they were producing. To put that in further perspective, The Who are in the Guinness Book of Records as the world's ever loudest rock group, with a recording at one of their concerts, actually at Charlton Athletic Football Club in the 70s, of 126 decibels. So bats are doing even better than The Who. Helen?
So why... OK, we know The Who are loud, because obviously their music sounds better that loud, I don't know. But why on earth do bats need to be that loud?
It comes down to physics, partly. These are insectivorous bats, and the fact that they're producing such high frequencies means that the sound is very rapidly attenuated or dampened down by the air, so it doesn't travel very far. So to get the reasonable range, and they found that the range of these bats was about 10 metres for their sound to penetrate into the air, you need to put out a big sound, because otherwise it just won't go very far. They are quite environmentally aware, though, these bats. They have a conscience, rather like you pulling into your cul-de-sac and dipping the headlights to avoid disturbing the neighbours. When they get near their target, they do turn the sound down a bit, so they are a little bit concerned for the welfare of other people nearby, or other bats nearby at least. But anyway, that's the first proper study, comparative study of insect-eating bats in the world, and how loud they are. No one had realised this before.
That's just awesome. I guess that's the same reason why elephants can communicate for a very long way, because they're very low, aren't they? And so their sounds can travel a long way, so it's the opposite end of that spectrum.
Yes, the opposite of a foghorn. You use low frequencies because they do travel very, very far, because the wave is going up and down over a much longer distance, so it's moving less air molecules, whereas the high frequencies are moving them up and down very fast a lot of the time, so the energy gets dissipated very fast, but with low frequencies it doesn't. So yeah, you're absolutely right, it's the opposite of the elephants.
Excellent. Well, how could I resist this week a fantastic story from the deep sea oceans with scientists this week who have been thawing out a colossal squid, and that really is its name. It's not just describing it, although it does describe it as well. Its name
Thawing out a colossal squid. That's a funny name.
No, just the colossal squid bit, honestly. Anyway, it's been in the freezer in the Museum of New Zealand Te Papua Tonga-Rewa in Wellington, and it's been actually on ice for a year since it was caught by fishermen off the Ross Sea off Antarctica last year. Now, we know hardly anything about these creatures. There's only been about 8 of them ever found, and most of them actually have turned up inside the stomachs of whales. Sperm whales tend to like to eat these creatures. This particular specimen weighed nearly 500 kilos, which was about the size of a young cow.
How big was it in terms of length?
It was, if you stretched it out, its tentacles went about 10 metres long. So
that's huge.
It is huge, absolutely huge. And they think they actually could grow bigger than that as well, perhaps up to 15 metres. And one of the really cool things they found, so basically they'd had it on ice all this time and then wanted to make sure that they could thaw it just slowly and well enough so they wouldn't all fall apart when they actually did take it off ice. And so scientists have been looking at it and trying to understand a bit more about these strange creatures. And what they found, one thing they found, is their eyes are enormous. Possibly the biggest eye. You talked about the loudest creature. This is the creature with the biggest eyes in the world.
Go on then, how big?
About size bigger than a football. And the lens itself inside the eye, which is spherical, is bigger than an orange. It's about the size of our head.
That must be because of the environment it lives in, Dave, in terms of its ability to gather light, I would think.
Yeah, like the bigger the pupil you've got, the bigger the lens, the more light you can get into your eye. So I guess if you live in a very dark environment, you're more likely to be able to...
Because they're really deep, aren't they?
They are
these
very deep.
animals?
Kilometres down they go down. That's partly why we don't know anything about them, because how on earth do we go down there to see them? I think it's the kind of thing we're more likely to discover more about if we stick cameras to whales and then get them to go and find them for us.
What do they eat, these massive squid?
We don't know. They've never found an intact stomach for one of these creatures, so we don't actually know. We think other squid eat each other, so it's possible it might be cannibalistic, but obviously that's not a staple diet. They will eat other fish, I should think, down there and those kind of things. Another thing they discovered, they thought this was a male, but it turned out to be a female, this particular specimen, because it had ovaries packed with thousands of eggs. So it really is rather funky, and they're going to keep looking at it, and then when they're done, it's going to be embalmed and preserved and hopefully put on display somewhere. Just to tell us a bit more about those fantastic things that live in the deep, dark, mysterious oceans.
Oh, cool. Now, I feel slightly underwhelmed on size. I feel slightly under-endowed at the moment, because now I'm going to talk about something much smaller. Now, it's been thought for 30 years or so that various animals, especially migrating birds, must be able to navigate through magnetic fields. Some experiments have been done on pigeons where you give them food in two ends of a room, and then you turn on a magnetic field if there's food at one end, hidden food at one end, or turn off if it's another end, and the pigeons they always go to the end with the food where you're telling them to.
So in other words, you can confuse them by putting them in a magnetic field. Whatever clue they're using to navigate, you can confuse it by magnetising them, which is why people think they use magnetic sources to navigate.
And you can kind of give them hints. If you hide food at one end of a room and then turn the magnetic field on, and you keep doing that, and then you turn it off, they'll go to the other end. So they can obviously detect the magnetic field. But
the key question is how, I guess.
Yeah, because no one's found any structures inside them which possibly could, and everyone has thought that chemical reactions couldn't possibly be sensitive to tiny magnetic fields like the Earth's magnetic field.
Because we're always saying the same about humans, aren't we? That how can we possibly be sensitive to a magnetic field? So what's the new finding?
Well, Peter Hoare and colleagues at the University of Oxford have in fact made the first chemical that's ever been sensitive to this sort of magnetic field. They've taken three other chemicals, a carotenoid, a bit like you get in carrots, a porphyrin, which is a bit like haemoglobin, and a fullerene, kind of attach them together, and when they get hit by light, it moves an electron, so one from the porphyrin to the fullerene and one from the carotenoid to the porphyrin, and then after a while those electrons move back again. They've been looking at this with infrared light. But if you put a magnetic field on them, it takes much, much longer for the electrons to move back again. And so this molecule they've made is very similar to other molecules called cryptochromes, which are found in birds' eyes. So it's quite possible that, because you can have this chemical effect on a very small scale, that the birds are using the cryptochromes. When light hits them with magnetic field, it'll react one way, but if there's no magnetic field, it reacts another way. So they might be detecting the magnetic field that way.
Because there was a study which was largely written off from Germany a long time ago, Berlin. Some scientists put humans in a dark room on a swivel chair, and they showed them a light bulb at different positions in the room, and they had it on a dimmer switch, and they would turn the dimmer up so the light bulb would come up gently, and they would ask people to signal when they could first see the light bulb. And they found, or they reported in this study, I remember reading it, that people could see the light earlier when they were lined up with the magnetic field than when they weren't. And so this was written off at the time as, it seems a bit dubious. But maybe there's some basis then if birds really are sensitive. And because our other senses are so dominant, we just ignore our magnetic sense. And in fact, we just rely on the other cues that we get from our visual system and our other kind of sense of where we are, road signs even. So we just ignore it. It
may even be possible that you could learn to use it if you were in the right conditions and you spent long enough.
Sure. Well, we'll just have to wait and see, I guess, where that one's going, won't we, whether or not that turns out to be true. But here's something that very much is true, and that's the problem of HIV. The UNAIDS figures at the moment make shocking reading. There's about 33 million people at the moment living with HIV or AIDS in the world, and the current death toll per year is about 2 million people. So we strongly need some kind of help for these people, which is cheap. the drugs we've got, antiretroviral drugs, are actually quite good at damping down the virus, but they never get rid of it from someone's body. And so there's a big push to try and find a better way to tackle HIV. Now, it turns out that there's a family of chemicals called phorbol and these are made by plants. We can also make them artificially, but they're quite difficult to make. And they're made by plants. There's one called DPP and another one which is called prostatin. And they're in families of euphorbia plants, which are natives to Australia and also Samoa. And looking into ancient Samoan traditions, there are some of these plants which have been used to treat viral infections in sort of local folklore. And it's because they've got these chemicals in. How do they work? Well, in the context of HIV, they reduce the density on the cell surface of receptors that HIV uses to cling onto cells. So when HIV wants to get in, it uses the viral equivalent of Velcro to cling onto the cell surface, these things called CD4 receptors and CXCR4. And these chemicals turn the expression of those receptors off, so cells are harder for HIV to get in. But their other major benefit is that they also make the virus come out of, when you add these chemicals to viral infected cells, they make virus that's hiding in the cell come out, because the thing with HIV is that it hides inside the genome of an infected person. So it gets into a cell and then inserts itself into their DNA and hides inside the genome for an undetermined amount of time and then later re-emerges again. So that's why you've always got this pool of virus to reactivate from, and we want to find out how to get rid of that. And these chemicals will flush out these viruses. They make the virus reactivate, because when it's reactivated it can be susceptible to drugs, and so scientists view this as a good way of treating the problem. Well, these chemicals are in very small amounts in these plants, very hard to make, but now scientists led by Paul Wender have got a paper in Science this week. They're at Stanford. They've developed a chemical synthesis method to make them in large amounts. They can make gram or at least milligram quantities of these chemicals. So this means that now scientists can begin to understand much, much better how they work, and therefore how to copy the bits of the molecules that actually do this antiviral effect, therefore making perhaps something that's easier to make but is equally good at doing this. And they also say a good bonus is it's been used in nature by Samoan healers for a long time, therefore these chemicals seem to be well tolerated by the body, therefore they're much safer.
Cool. I was just wondering, when it flushes it out of the cell, does it actually get it out of the genome, or does it just make it obvious that that cell has got the virus so something else can kill it?
The virus never leaves the genome, but it makes the virus disclose itself so that then drugs which can target that cell can kill it and therefore take the virus with it, because all the time it's hiding inactive inside your genome, you can't touch it because you can't tell that bit of DNA from your own.
Cool.
Well, I was talking earlier about squid and the wonderful things in the ocean, but unfortunately, of course, there is so much bad news coming from the oceans at the moment, and this week is there's no difference there, because we have a story from a scientist at the University of Kiel in Germany, led by Lothar Strammer, who've been studying the so-called dead zones of the ocean, and these are found to be getting alarmingly bigger. Now, these are the areas where there's very little oxygen, which means that most ocean life, including fish and those one fantastic colossal squid, aren't able to survive. They're basically the equivalent to the deserts of the ocean. Now, we've known for a while that shallow seas that get input from land, like nutrients and pollutants, that's where these dead zones can happen. So particularly in places like the Gulf of Mexico, there's been a really large dead zone. But now Strammer and colleagues have revealed that at intermediate depths, so around 300 to 700 metres, there's also an expanding mass of oxygen-poor water. And they're using data from research vessels as well as from special fixed buoys that are equipped with oxygen sensors. And they've discovered that over the past 50 years, areas of ocean that used to be full of oxygen are now really becoming what they call oxygen minimum zones, where there's just not enough oxygen to support so much life.
Do they know why this has changed?
Right, well, this is the big question. We don't know for sure, and there is natural variation caused by things like El Nino, which we know about. But unfortunately, of course, the finger of blame is pointing squarely at global warming and rising sea temperatures, because the warmer water is, the less oxygen it holds, and also it won't sink down. The idea of, usually in the oceans, you get this circulation of cold, oxygen-rich water that sinks down, bringing oxygen into lower depths. And if it's too warm, that's not going to happen so much. So it could be that. And the good news is, I suppose, that fish can swim away and escape these dead zones. But if those zones are getting bigger and bigger, perhaps there won't be anywhere left for them to swim to.
It's all very well saying they could just move away, but the thing is, that's a bit like brushing dirt under the carpet. It doesn't make the problem go away, does it? We really need to tackle why we've got this problem in the first place.
Absolutely, yeah.
Thank you, Helen. This is The Naked Scientist with Dr. Chris, Dr. Dave, Dr. Helen. It's our science Q&A show this week, where we are asking you to come in with any questions you would like us to try and solve. But before then, we've got Kitchen Science on the way. This is your chance to go and grab an elastic band and your face, because Dave has got an extraordinary observation of rubber behaving badly, and that's on the way.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
You're listening to The Naked Scientists. Now, still to come, we'll be taking on some of your science questions and meeting a new Teletubby-type robot that could keep children company in hospital. But first of all, we've got kitchen science right here, and with Dave in the studio to explain what we are going to be doing. Hi, Dave, what do we need this week?
OK, this experiment is ridiculously simple. All you need is a large elastic band. The bigger and fatter, the better. And you want something to be able to sense temperature quite sensitively, and you've got one of those quite conveniently in your lips. They've got very thin skin, so you can sense temperature quite well on them.
Okay.
All you've got to do, it's ridiculously simple. Take the elastic band, hold it to your lips so you feel the temperature, then stretch it quickly, and then feel the temperature again, and then wait for 10 or 15 seconds, and let it shrink again quickly and touch to your lips and see if the temperature's changed. If you notice anything interesting happening, give us a call.
And what about if the elastic band snaps in your face?
You probably might want to test it once or twice in case if you've got a dodgy-looking elastic band.
Because that will feel rather hot, won't it? It'll certainly throb if that
Painful,
happens.
certainly.
OK, so elastic band's all you need, but watch out, don't flick it in your eyes or anything. We don't want any disasters happening at home. But take it, have a go, and if you have any answers, to let us know. Chris at thenakedscientist.com.
Josh is on the phone. Hi, Josh.
Hello.
Welcome to The Naked Scientists.
Yeah, hello. My question is, I'm just wondering, what happens when a neutron star collapses, and what happens when a black hole collapses?
OK, so first off, what are they for people at home? A normal star is a big ball of gas. It's actually held up because it's really, really hot. It's held up against its own force of gravity because it's really, really hot. In the same way that when a gas is hot, it expands. The star's temperature allows it to expand and stay fairly big. But when the star gets really, really old and it can explode, and eventually it cools down a bit and it starts to collapse under its own gravity. And stars which collapse enough, they crush the protons and electrons together to form neutrons. And then these form, basically they form huge nuclei of atoms, a whole star-sized nucleus of atoms. It's basically just neutrons. And so that's what a neutron star is. So a normal star can collapse into a neutron star. Now, if a neutron star slowly gathered more and more mass, then it could collapse again, whereby the neutrons couldn't support themselves. They start to get crushed together, and it would get so heavy it would turn to a black hole. Now, this is the heaviest astronomical object we know of. Basically, that means that nothing can escape from a black hole. There's so much matter in there that even light can't escape. If a neutron star could collapse, it would turn into a black hole. It would need to get heavier. It needs to get above a certain mass to turn into a black hole. We don't really know what's inside a black hole. We only can describe it using the equations of gravity, so we don't really know anything about the structure inside of it. So as far as we know, there's nothing. A black hole is the final degree of collapse that we know of. So a black hole would only collapse into form a bigger black hole as far as we know.
There you go, Josh.
Oh, thanks. That was really useful.
Does that help?
Yeah, it did.
I didn't know black holes and neutron stars are on the GCSE syllabus these days.
Oh, I'm not doing GCSE.
I'm not surprised, because I think that's not even on the degree syllabus anymore, is it?
I don't know. I'm only 12 though. So
no, I'm joking. It's okay. So are you interested in space science in particular then?
Yeah, I like nuclear physics especially.
Fantastic. So that's where you see your career lying, is it?
Yeah, hopefully.
Brilliant. Well, thanks for joining us on The Naked Scientists.
Yeah, thanks for ringing.
All right then.
Bye.
See you shortly. Quick question for you, Helen. This one comes from Melissa, and she says, during the winter, I put blocks of suet with seeds in them out for the birds. It only takes the birds a few minutes to find them and dig in, but increasingly I've become very disturbed by the whole thing. Suet, it seems, is animal fat, so apart from the alarming idea that I'm promoting carnivorous behaviour in chickadees, it raises a much more fundamental question, which is, how do birds recognise the fat balls as food when they don't look like their natural food at all?
Well, birds are actually quite adaptive when it comes to people and the kind of foods we can give them. Here in the UK, there was a wonderful phenomenon that happened since 1921, a thing we no longer have, which is glass bottles of milk sitting on our doorsteps, and milk that isn't homogenised. So actually, if you had full-fat milk, you had this wonderful creamy chunk floating up to the top. And for the first time in 1921 in Southampton, someone saw a blue tit pecking at that top, the silver foil top of the milk bottle, to drink the cream. And now, if that doesn't any more unnatural a food source for birds, I don't know what is. And what actually happened, and in fact, people studied how this behaviour spread around England by the 50s and 60s. Birds all the way across England had learned how to do it, and it almost seems like it kind of came to a new area, and all the birds in that area would learn how to do it, and it was this phenomenon that spread around. So I think birds do know how to adapt very much to different types of food that we give them. Suet, I think, think is actually meant to be a very good food for birds, especially in winter. The RSPB here in the UK, the Royal Society for Protection of Birds, on their website they do recommend putting out suet. So I don't think that's a problem. I think birds can eat other animals. It's all right, but I understand your concern. So I think birds really are quite adaptable. They'll have a go, and if it tastes good and they realise it's got nutrients and energy in it, then they'll take it and they'll eat it.
Worth bearing in mind that the birds are the closest living relatives of probably the most fearsome man-eaters of all time. Well, not man-eaters, but meat-eaters, and that was dinosaurs,
Absolutely,
of course. So it's not surprising they should be adapted to eat meat. Dave is on the line. Hello, Dave.
Hi, Chris. You okay?
Very well, thank you. What would you like to talk about?
Well, it's about the temperature of space, actually. I'd like to ask, why is space so cold? What makes it cold? And is there an average space temperature?
That's actually really quite a deep question.
A
deep space.
In deep space, indeed. Okay, so space is originally, if you go back to the Big Bang, if you look in any direction, you'll see something. And if you look in any direction far enough, there's no stars or anything in the way, you'll see the kind of big soup of atoms which were created after the Big Bang. And this light was emitted when basically electrons were collected by hydrogen atoms. And when they did that, they released lots of energy and photons, very high energy light. And this is well into the gamma rays. Now, because the universe has expanded so much, these gamma ray photons, which are incredibly hot, like thousands and thousands and thousands of degrees centigrade, have slowly been stretched as the universe has stretched. And their wavelength has got longer and longer and longer. And with that, they've got colder and colder and colder because longer wavelengths are lower energies. And so they got stretched so much that their temperature is about 2 or 3 degrees above absolute zero, so about minus 270 degrees centigrade.
But if you're in direct sunlight in space, it's actually pretty hot, isn't it? Because the astronauts working outside the space shuttle in space when they go for a spacewalk have to be pretty careful because they can just get frazzled.
Yeah, the sun is incredibly strong, so if you're in direct sunlight, then the temperature sort of feels like 200 or 300 degrees centigrade. But if you're away from, if you look at the piece of sky with nothing in it, it will look at about 2 or 3 degrees centigrade above absolute zero.
So there you go, Dave. That's how you do a space forecast.
Excellent. Well, that's that problem solved.
All right. The answer is it's cold everywhere except in direct sunlight where you get fried.
Yep, of course. Thank you.
Thanks for joining us on The Naked Scientist.
Thank you. Bye.
Dave Scally, if you'd like to join us, email chris@thenakedscientist.com. And if you're in another time zone, you can leave a message on our answer phone, which is exactly what Matthew did.
Hi, Matthew calling from Sydney in Australia. And I have a question in regards to evaporation, and specifically the evaporation of solids. Now, that sounds like a strange question, but the reason I ask is because I have ice cube trays in my freezer, as I'm sure most people do, but I don't use them all that often. And when I come to get them out over, let's say, a few months' time, it seems to me that the level of the ice in the ice cube trays is much lower than when I filled them up with water maybe a month or two before. So my question is it possible that that ice is in fact evaporating slowly into the atmosphere of my freezer? Thank you.
Well, I wish I was there in Sydney because although it's going into wintertime now, it's certainly a lot warmer than it is here. But this is a really good observation and it's absolutely true. Your ice cubes will lose volume in your freezer over time. And the reason for this is although they're frozen and literally water molecules have been joined together to form ice, what actually is going on, if you could zoom in with a very powerful camera and watch the energy in ice, is that the ice is sharing out all the energy, even though there's a lot less of it because it's cold, amongst all the water molecules, and it's random. So every so often there'll be some water molecules that have enough energy to vibrate or escape their way free from the surface of the ice. And at the same time, others will rejoin onto the ice, and so this is what's called a dynamic equilibrium. But every so often, you'll get a molecule of water which will gain enough energy to spring off of an ice cube, and it might well form some ice elsewhere in the freezer or just fall out of the door. So over time, where you've got a lot of something, water as ice, it will slowly diminish and shrink and it will disappear. So it will deposit around the inside of the freezer, but because the freezer has the door open from time to time, you're going to be losing water as well that way. And some water goes in at the same time when you open the door if you've got a stuffy room. But basically it's because there's a dynamic equilibrium going on with some of the ice losing water molecules as they gain little bits of energy.
The same process actually happens in reverse to form ice snowflakes, because snowflakes are actually formed by, it's called sublimation, this process, water vapour sublimating to form ice crystals directly without going through a liquid, otherwise they'd be little balls. So they go straight to form ice crystals and you actually get the beautiful crystals in snowflakes.
Good answer. Thanks, Dave. And thank you very much, Matthew, for a great question. Helen, quick one here for you. This is from Clive, and he says he lives in South Africa, where there are very few houseflies to be seen in the winter time, but there are some. Do most of them hibernate in the colder winter months, or do they move to warmer climes? So, in other words, do houseflies as well as humans go to warmer weather?
No, I don't think flies do go on holiday. They don't migrate. Flies actually, they only live for a maximum of about 2 months, but usually only about 15 to 24 days. So there's a possibility that some of them might hang on into winter, but they generally do much better when it's warmer. But they can survive over winter, and that's actually another stage in their life cycle, which is as larvae or pupa. So what happens with flies is that they will lay eggs, which hatch into larvae, otherwise known as maggots, which is lovely. They will be all right when the temperature drops, and they will hang around in food and feces and things like that. Lovely. If you've got a big pile of horse manure in your garden, they might hide out there. And then they will then grow.
You've got a huge pile of horse manure in your garden?
I don't have a garden, actually, Chris, but if I did, I would. It would be my compost heap. Anyway, and the larvae grow, and then they will pupate, so they kind of wrap themselves up in a tight little packet, which will then, they can sit around and survive the winter, and that hatches into an adult. So the adults you see in the winter, I think you also notice they're quite slow, aren't they? And they don't fly so quickly, much easier to swat. They're really just the tail end of the sort of summer population and waiting to kind of regrow again in the springtime.
So all the buzz about the science of flies here on The Naked Scientists. We are, of course, also live in Second Life, if you'd like to join us there. And also thank you to Law Gynoid, who's in Second Life, and complimented Matthew's question on his ice cubes evaporating. Says, what a sublime question. I suppose it also goes for your answer, Dave. So thank you very much for that. Now, soon we're going to be catching up with our technology correspondent, who's Chris Vallance, who joins us every month. He met Mira earlier this month for a chat about a website called Twitter, which is all the rage. It's the new Facebook, they say. But earlier in this week, I caught up with the Naked Scientist contributor Chelsea Wald, and she's currently in Belgium, where she's been to hospital, not for a bad thing, she's not ill or anything. She went to meet an unusual character who's actually going to be cheering up sick children there.
Hi, Chris. I have someone I'd like to introduce you to. Dr. Chris, this is Probo. Probo, this is Dr. Chris.
Well, if I'm honest, Chelsea, that doesn't make an enormous amount of sense to me, what he's saying.
Well, that's because Probo is not speaking any real language. This is, in fact, a nonsense language unique to Probo. You see, he's an intelligent robot being developed at the Flemish Free University of Brussels. When he comes together, he's going to interact with sick children in the hospital. The language they're developing for him is something like the Teletubbies, in that it doesn't really mean anything specifically, but it has emotional meaning.
So can this robot respond to the children and react to the way that they behave with him?
Yes, exactly. The idea is that Probo will help children by reading their emotions through their facial expressions and their tone of voice, and then Probo will respond in some sort of comforting way. That could either be by mirroring the kid's emotions, like anger or fear, or by expressing a different emotion, like contentment. Psychologists will work on that part.
So what does he actually look like, Probo?
Well, that's an interesting question. Probo's designers put him in the order of Proboscidia, which also includes elephants, mastodons, and mammoths. But basically he's green, he stands on 2 legs, and he has a trunk. He'll also have an interactive video display in his belly that could allow the child to talk to his family and friends. This is what the person who came up with the idea of Probo, Ivan Hermans, has to say about the video screen.
I think it will be a tool of communication in the future. Because when kids are going to the hospital, they cannot go to the class anymore. They miss their environment. And that will be a tool of communication. I think that's very important, that they can speak with the grandparents, with the school. When you have to go to a hospital, they cut all the social contacts.
The video screen will also provide a new way for the doctors to interact with the child. For example, asking how much pain the child's in. The kids might also get information about the procedures they're about to go through. In effect, the idea is that Probo will eventually be like a psychological counselor, as well as an entertainer and a companion. Here's Ivan Hermans again.
I think because the robot will be there 24 hours. And sometimes when a child is not feeling well, you want to be alone, I think. Not with the parents, not with the doctors. And with the robot, he can be like a companion. I think that's important.
So what stage of development is he at now, Chelsea?
Well, Probo is still in a pretty early stage. They hope to have the first prototype in hospitals by the end of this year, but he will still have some sort of operator, like a puppeteer, so we won't have his own artificial intelligence in place yet. They just recently got the first full-size body, which is basically just a stuffed animal body. Now they're going to rip into it and put the moving parts inside. They're doing all the robotics on the principle of compliant actuation, which means basically that the parts aren't rigid. Everything is designed to be soft and safe for kids. So if the kids grab at his trunk, for example, it will bend very easily, but it will go back to its original position when they let go.
Which is, of course, very important. But is this just for the hospital market? Because I can think of lots of parents who would probably quite like some kind of companion for their children when they're unwell.
Yeah, that's certainly a possibility, though at first someone would have to be pretty rich to buy one of these, I would think. But they're also thinking that Probo would be helpful for caring for the elderly, though they think they'll have to design a new appearance for him. Kids really love the way he looks, and in fact they helped design Probo, but older people seem to find him a bit too strange.
So you think more the Florence Nightingale look for the elderly consumer then?
Possibly. I don't know, maybe a purple hippopotamus, or who knows.
Purple hippopotamus? Well, if it's working in a care home for aged hippies, that might be ideal. That was Chelsea Wald introducing Probo, a friendly, cuddly robot who'll soon be helping to help make staying in hospital a bit more fun for young people. Thanks, Chelsea.
Thank you very much, Helen. It's Chris, Dave and Helen as The Naked Scientists, and we're taking your science questions and answering them for you. You can email chris@thenakedscientist.com. Richard's in Milton Keynes. Hello, Richard.
Hello.
What can we do for you?
Well, I was wondering about big black holes, and whether or not before the Big Bang, whether there was a big black hole there.
Well, no one actually knows what preceded the Big Bang. All we know is that when the Big Bang happened, there was this massive amount of energy from a source that was infinitely tiny and infinitely powerful that just blasted out all this energy all at once, and space popped into existence. Before the universe existed as the Big Bang, there was no universe, and so as far as we know, nothing existed before the Big Bang, strange as it sounds. What do you think, Dave?
Yeah, I mean, all we know is that everything's expanding very fast. We know some things about how it's expanded over the last 15 billion years. We've got very little evidence very close to the actual Big Bang, apart from the distribution of matter in the universe. But actually knowing what happened beforehand, who knows, basically.
Although it's fair to say that the Large Hadron Collider at CERN, which is hopefully going to switch on this year, is going to be colliding particles together at very high energies. And what scientists are hoping to understand by doing that is basically the process by which energy turns into matter, because that's what the big fundamental thing about the Big Bang was. There was a lot of energy, but no matter, no substance, no stuff, the material that you see in the world around you, and somehow that energy got converted into matter, and that's what scientists are hoping to achieve by slamming things into each other at high energies in CERN. So I think we just have to watch this space. Sorry, Richard, for that pun.
That's all right. No, we don't know what was there before, but I just imagine there's a tremendous amount of matter there.
Well, that's the point, that there was no matter, there was just energy, and that's why scientists need to understand how energy turns into mass, because we know the two are interrelated in some way, and Einstein's famous equation E=mc² kind of gives us a clue towards that, but exactly how that interchange occurs is we're just grappling with, and that's hopefully what scientists in Geneva will find out with this multi-billion-pound experiment that they're setting up there.
So we don't know everything then?
No, unfortunately there are still lots and lots of questions to answer.
Right, I shall come again with another question you don't know.
Thank you, Richard. See you soon.
Bye.
Richard in Milton Keynes. Now, Helen, here's a question for you. Is there a metabolic cost, asks Gary Stab, to the generation of bright colours in animals?
It's a very, very good question, and you're absolutely right. So there are pigments that lots of animals use for showing off, usually to attract mates. That's generally what it's all about. And these are molecules that, they're quite costly to create, not to mention the fact that you also look more obvious to things like predators. But this was a question that a guy called Jeffrey Hill looked at. He's from Auburn University in Alabama, and this was back in 2000. And he looked at house finches, which basically they're birds that can grow colourful feathers in yellows and oranges and reds using carotenoid pigments, similar to what Dave was talking about earlier. And what he did was he actually fed a bunch of house finches with these types of pigments in water, and then he fed half of the birds lots of food, so they were nice and happy, and they could lay down food, and basically they were doing great. And then the other half, he restricted their diets, which wasn't so nice, but basically wanted to know what the difference was when they did and didn't have enough food to eat. And as you might imagine, the ones that didn't get enough food basically were much more drab than the ones that had lots of food, who grew lovely, bright, shiny, colourful feathers. So I think that's a really good way of showing to us that, yes, producing pigments is expensive on food, and if you haven't got enough food to do that, then you tend to not be able to produce such brightly coloured feathers.
Thank you very much, Helen. So that's a bottom line is that Joseph in his Technicolor Dreamcoat was definitely the way to go. Dave, here's one for you. It's from Greg Dean. He says, when we're looking at an image of an individual atom, as in when IBM posted that amazing picture in 1990 with IBM spelled out in xenon atoms on a surface. What are we actually seeing? Photons, electrons, protons, neutrons? What actually was that?
That kind of image was probably from a tunnelling electron microscope, scanning tunnelling electron microscope, whereby you get a very, very, very sharp point, which is down to where it's so sharp it's probably only got one or two atoms on the end of it. Then scan that very slowly across the surface of a material. And then with the scanning tunnelling electron microscope, you measure the amount of electric current going between that. You apply a little tiny voltage, measure the current between that tip and the surface. So you're actually sort of measuring the resistance of the surface. There are other similar images where you can actually just measure the force on that tip. So you're basically measuring the force between the end of the tip and the surface in the bottom. And if an atom's higher up, the force will go up.
So with the xenon, what you're measuring is when the electrons whizzing around the xenon get near the electrons of the tip of the microscope, it can measure that current and build up a profile, basically. So what we're seeing is a totally contrived profile. That's not a real picture of those atoms. It was effectively a pattern of how the charges are moving around.
Yeah, it's a pattern of how easy it is to put electric current into the material. Okay, cool. I've got a question for you here, Chris, from Emil in Dubai, which is, why does your stomach get left behind when a lift or aeroplane drops?
Yes, I've had that experience lots of times. So aeroplanes suddenly drop and you feel almost weightless. So you are almost becoming a bit weightless. But the reason is that your guts and your viscera are quite heavy, and they're also hanging inside you. So your stomach hangs down below your diaphragm and it's connected to your guts. And so everything is pretty much mobile. And if you do an operation on a patient, it's always amazing to me when we used to open people up for, say, appendicitis or something, and you can see the guts all kind of writhing around themselves. But not dramatically fast. I mean, it's not like a snake pit or something, but you can actually see them moving. And so everything is mobile. It's got to be like that to enable things to move, because of course the guts need to stretch to take in things and then shrink again when things move through them. And of course, because it's all not fixed inside you, if you go over a bump, when the vehicle, the car or the aeroplane drops on the other side of the bump, your body is a bit left behind for a little while, and there's enormous numbers of stretch receptors and vibration-sensitive nerve endings in your guts. That's why people talk about having a gut feeling for something. It's very true. A lot of the frequencies that we get from the world around us, the low-frequency vibrations, are felt in your abdomen, and you think you're sensing them from all over your body, but enormous amounts of that information comes from your gut. It's a gut feeling, quite literally. And because those stretch receptors get excited when your guts are literally fly up in the air with your body moving down around them, as a result, it does feel like you have a sort of sinking feeling. The other reason you get a sinking feeling is because you might get a bit frightened. Now, when an aeroplane suddenly drops, you can have that moment of terror thinking, oh my God, is the plane going to fall out of the sky? And what happens then is that you get a little surge of adrenaline. Your sympathetic nervous system kicks in a very big way. That's the part of the nervous system that gears you up for fight or flight. So you're either going to run away or have a big fight with somebody. And that produces lots of adrenaline, and adrenaline powerfully switches off your guts, because the one thing you don't want to be doing when you're trying to run away is wasting blood supply feeding your guts. You want the blood going to your muscles and your lungs and every other part of your body you need to run away or fight. So you turn off your guts, and that turn-off signal does feel like that sinking feeling or the butterflies you get in your stomach. So it could be possibly a combination of the two effects, I reckon.
I guess that when you're standing normally, all those stretch receptors, they're being stretched by the weight of the guts, and then if you start falling, because your body's falling at the same rate as your guts, then they're going to stop being stretched, and then they're going to think that's very strange.
That's probably part of it, but I think probably the adrenaline is probably an additional thing that makes you feel, oh, what on earth's going on? But yeah, it's certainly an unpleasant sensation, isn't it? Dave, quick one for you. This is from Jeff Seldenbridge. He's in Nevada, and he says, I'm not sure how to pose this question. I'm going to ask you this thing. It says, if I created a box about 0.5 metre side and I made it out of ice 3 centimetres thick, I put a thermometer inside this sealed box and put it in the Arctic, would the thermometer inside register 0 degrees or something else?
If the sides are just made out of solid ice, then it will behave like a box made out of anything else. It could be a box made out of stone or anything, and slowly over time it will cool down to the same temperature as the environment around it. However, if you had a box of ice filled with water, then instead of the water cooling down when heat is taken out of it from the cold environment outside, it will create ice. So slowly the water inside will freeze, and as long as there's water in there, that water can't be much below 0 degrees centigrade. So if you had a box of ice full of water, then it would be 0, but as soon as it freezes, then it could get below there.
Thank you very much, Dave. Very quick one, Helen. Law Gynoid from Second Life says, do those drab birds you were talking about live longer because they're putting less energy, presumably, into making themselves look gorgeous?
Oh, well, I don't think so. I think the point is that they're not doing so well anyway because they've got less food. So in nature, I suppose, if they did want to live longer, by not having such fancy feathers might give you a bit of a helping hand. But that's something I think we need to study as well. But because this was in a lab, I think the guy was basically just keeping those poor creatures a bit hungry. So no, I don't suppose they would have lived as long.
I wonder if the same thing applies to humans. The ones that make themselves look gorgeous also live longer. Thank you very much, Helen. It's The Naked Scientists with Chris, Dave and Helen. It's our science phone-in extravaganza, and if you've got a question for us, email chris@thenakedscientist.com.
Stripping down science.
OK, let's do it.
The Naked Scientists.
Very soon we'll discover how the Olympic torch keeps burning on an aircraft in our question of the week. But first, we sent Mira to meet up with Chris Vallance for a chat about microblogging websites called Twitter.
Well, it's time to catch up with the latest developments in the world of technology. So once again, I've come down to London for a coffee with our resident expert, Chris Vallance. So Chris, there seems to have been a lot of chat about this site Twitter, but what exactly is it?
I think Twitter is the new Facebook, that's the buzz. But what is Twitter? Well, Twitter is a way of posting short epigrammatic messages online, 140 characters or less. It's called a micro-blogging format. Basically allows you, via instant message, via the web, via your phone, to blog little short messages answering the question, what are you doing? And share those posts with your friends, with people who follow you online. It's a very short, simple way of posting stuff to the net, and it's got a lot of buzz lately. Now, it did launch quite a while ago, but since then it's grown. It's become something of a global phenomenon.
But it's not just the one site now, is it? It seems to have branched out into quite a few side projects.
One that I quite like is called Twitter Local, and what it does is it lets you see all the posts, all the little messages people have written in a particular area. Now, this is fascinating because you can explore the whole globe in this way.
I live and work in Afghanistan. Twitter lets me share information with friends and colleagues quickly. If there's any sort of trouble, I can send out a quick warning. The other morning, there were about 10 or 12 loud explosions that shook Kabul. So I sent out a tweet asking for information from my friends. And a couple of minutes later, I was able to get a reply. Turns out the explosions were just the army practicing for Independence Day.
As I'm sure you know, there have been these riots happening in Egypt and around the world due to rising food prices. We got apprehended physically by these police officers and taken to prison. I had set up ahead of time sort of an emergency call in my mobile to send a mass SMS to my Twitter and to my Egyptian friends. As soon as I was apprehended, I sent the word arrested to that whole network, and being able to raise that awareness and to let people know where I was saved me from sort of disappearing into a black hole.
I divide my time between the US and India. I find that Twitter is a strong digital umbilical cord for me. Interestingly, news channels in India appear to have discovered Twitter. For instance, there is IBN Live that has started a Twitter feed. And so that's a great way to find out what is happening in India.
So we heard there from Kevin Toomer in Afghanistan, James Buck in Egypt, and Kamala Bhatt in San Francisco and Bangalore. Now, as you heard on the tape there, James Buck actually used Twitter. He was in Egypt. He is arrested by the police. He twitters the word arrested, and his friends spring into action and raise the profile of his case and gets legal assistance. I mean, it's an interesting site. Again, I think the sort of the analysis of trends on it is quite interesting.
This kind of thing has spread out to other social networking sites as well, though, hasn't it?
Well, we spoke about Facebook earlier, and there's a new service for Facebook launched April 15th called Lexicon that lets you search people's wall posts for popular terms and graph those. So, for example, I put in BBC and Wikipedia to see what was more often cited on people's Facebook profiles. Turns out Wikipedia just about edged us.
That surprises me, actually.
Well, I think, obviously, Wikipedia links back to a lot of other news sources, so you could sort of argue the toss that way. Getting back to Twitter, we're starting to see a sort of an explosion in these kinds of services built on the data that Twitter generates. There's a lovely one called TwitURL, and what it does, it's the most popular links on Twitter, so you can see what people are linking to in their posts most frequently. One of the most popular was another service called Twitter Twerp Finder. As Twitter grows, more and more spammers, people with a commercial interest, are jumping in as well. And that was a service that helps you try and identify who the spammers are on Twitter and knock them out of your list of friends and followers.
That's quite useful.
Yes, it is, although it's quite a crude way of calculating who is a twerp in their language. So it'll be interesting to see how it works longer term.
It certainly will, and it's very nice to know all the new ways of identifying twerps. I'm quite good at identifying twerps in my life, but I don't think Chris Vallance is one of them. He was talking to our own Mira Synthlingham.
Thank you, Helen. It's The Naked Scientist. Don't forget, we've got a kitchen science experiment for you to take part in. Dave, very simple. What do you want people to do?
Basically, I want you to grab a large elastic band, feel how warm it is on your lips, stretch it as much as it'll go, but without breaking, then feel how warm it is then let it shrink, feel how warm it is, see if there's any difference.
Now, here's someone who's definitely not a twerp, but do you Twitter, Diana?
I think I'm still stuck on the older generation of chat clients. Do you, Chris?
No, I don't actually, but maybe I will, now I've heard all about it.
Well, maybe if I've got a burning issue to discuss with someone, I might take that up. So here is another burning issue.
My name's Graham Watson, and I come from South London. And my question is occurred to me when I was listening to the Olympic torch being discussed recently. I was wondering how you transport a naked flame on an aeroplane. It has to be a naked flame, I think, to continue the Olympic spirit. But even without the current security situation, surely it must be quite difficult. But it's obviously possible, so I wondered how they did it.
So according to a mix of old and new tradition, the Olympic flame must not go out until the Games are over. So how can you get it through customs, stick it on a plane, and does it have its own business class seat?
Hello, my name's Jordan Parham. I'm part of the team that worked on the Sydney Olympic torch and also the Athens torch and Asian Games torch 2006. How they keep the flame alight on the aeroplanes and therefore continuous along the whole relay journey is in miners' lanterns. These miners' lanterns are specially designed to maintain a small flame alight in all wind conditions, and they actually carry 4 of these lanterns at a minimum as backup flames for the mother flame at all times during the relay. When they take the flames onto an aeroplane, the miners' lanterns are approved prior to taking them on by the commercial airline or by the chartered airline, depending on how they run the relay, and they are then stored in an appropriate vessel. In the case of the Sydney Olympics, that was in a specially designed seat, and in other games such as Athens and the Asian Games, they used specially designed storage racks on the side of the aeroplane. And these miners' lanterns don't create any emissions. The fuel is a methylated spirits type one, which is fairly clean burning. Don't create any risk to any other occupants, and that's how they keep the flame alight on aeroplanes.
And that was Jordan Parham, who has actually built previous Olympic torches. So a miner's lamp has a gauze cage which surrounds the flame and allows oxygen in, but the gauze even absorbs the heat of the flame so that any flammable gases in the surrounding atmosphere won't reach ignition temperatures. So you can take the Olympic flame safely just about anywhere. Sometimes it even gets its own seat in storage racks.
And a listener in Second Life came up with the answer of Davy Lamp, as did another someone on our forum.
So the protests surrounding this year's flames have been pretty noisy. So here's a question involving earplugs.
My name is Bullfrog, and I'm calling from Illinois in the USA. I noticed that at times when I'd put earplugs in to deaden sound from outside, that worked really well, but then the sounds inside my head, they seemed a lot louder. Like chewing or humming or even breathing was really loud. And then I noticed listening to podcasts with the earbud-style headphones in my ears that I couldn't chew breakfast cereal and hear at the same time, whereas if I'm listening to a conversation without anything in my ears, it's very easy to hear and eat at the same time. So I was wondering, why is it when you have earplugs in or headphones like that, are the sounds from inside your head so much louder?
So I don't know if you've ever heard of an elderly and deaf dinosaur, but how can we know how old a dinosaur can get?
Hello, I'm Bert Lattimore. I'm from Virginia in the United States, and my question concerns dinosaur ages. Somewhere I heard that the big plant-eating dinosaurs could live up to 1,000 years. On another program or podcast, I heard that tyrannosaurs only live 20 to 30 years, which seems very brief for such a big animal. So I'd like to know, how long did the big dinosaurs live, those individual dinosaurs, and how can you tell from a fossil how long that animal lived?
So what exactly do earplugs do to your hearing, and how can we estimate a dinosaur's age? Join the debate on our forum at thenakedscientist.com/forum, or send your answers to me at questionoftheweek@thenakedscientist.com.
Thank you very much to Diana O'Carroll for this week's Question of the Week. So you're not a dinosaur, Diana. How long are you going to live? No, I'm only joking.
I'm a dinosaur.
Exactly. Thank you very much.
The Naked Scientists. Brought to you by thenakedscientists.com.
It's The Naked Scientists with Chris, Dave and Helen, and now it's time to find out the answer to this intriguing kitchen science experiment. So just remind everyone, Dave, what you were doing with this.
Well, I'll give you a rubber band and you can do it too, Chris. So there's a rubber band.
Here we go. Okay, what do I have to do with this?
Okay, so you want to hold it, touch
against
your
my lip.
Against your lip so you can feel the temperature. Just
Yep.
move it away slightly and then stretch it quickly. And then feel it again.
Yeah, okay, I've
feeling
looked
a little
that,
bit of difference in the temperature, and then let it leave it there for 5 or 10 seconds, then let it shrink quickly.
Ooh.
Feel the temperature.
Now that's pretty amazing. Okay, let me tell you, this is what I found, and you can tell me if I'm right. When I stretched it, it was hot. When I let it go and then touched it back on my lip, it was definitely colder again.
It was colder than it started.
Yes,
as well.
definitely.
Yeah. Okay, so what's going on? Okay, rubber is made up of very long molecules called polymers. These great big long pieces of string, and occasionally they're sort of tied together. So you like big messy net, incredibly randomly higgledy-piggledy net. These molecules are long, maybe like 1 million times longer than they are across. So huge, great long bits of string occasionally tied together. And then normally they're all higgledy-piggledy, but when you stretch it, you kind of straighten them out. Okay, and straightening them out kind of forces them to get close together, and that puts energy into them, so they start vibrating faster, and that makes them hotter. And then if you let it sit there when they're stretched for a while, then that extra heat will leave just into the air, and so they'll cool down a bit to the room temperature again. And when you let it shrink again, they've got to do work. The thing which makes it shrink is the fact that they're vibrating, and it bashes the long molecules into being less straight and be more higgledy-piggledy, and that uses up energy, and so that energy has to come from the temperature, so it makes it colder, so it cools down as it shrinks.
It's kind of counterintuitive, because you'd think it's doing work to shrink, and therefore it should get hotter.
But that work is coming from the heat, so it gets colder.
So it's a bit like when you put salt on an ice cube, really, isn't it? Because that's why the ice cube temperature goes down. When you put salt on it and it melts, it makes water at a colder temperature.
Yeah, because you need energy to melt the ice cube, so that energy's got to come from somewhere and it cools down the ice cube.
So apart from putting ice on the roads on a cold day, what's the sort of real-world example of this elastic band experiment? How does this apply?
I mean, the reason why rubber is stretchy is all to do with the structure. So if you didn't have anything with the structure of these very long molecules occasionally tied together will be elastic. You can get, if you cool it down far enough, though, the molecules stop vibrating enough to move past each other, and so they actually all kind of lock together, and a rubber will actually freeze. You've probably got it a bit colder than your freezer.
I saw someone put a rubber coil in liquid nitrogen once, and it just became solid, and they hung a weight on it, and nothing would happen. And then as it warmed up and took in energy from the environment, then it began to bounce like a spring again.
Yeah, and it's the reason why rubber seals and things, it's like the Challenger Space Shuttle.
I was going to say that blew up because of the rubber O-rings getting too cold.
Too cold, and it stopped being flexible, and so it couldn't bend and keep the hot gases inside, and it leaked out the side. And
is there any way you can add chemicals to the rubber to reverse this effect, or stop it behaving in this way, or get around that problem?
I mean, if you can stop it being elastic but if you tie the rubber together so often that it can't stretch at all. In fact, natural rubber is far too stretchy. It's very, very soft. And in fact, they for car tyres and most rubbers, they add a little bit of sulphur to it, which tends to tie them together and makes it much stiffer because you get less length between the places where it's tied together. So it's still slightly flexible, but not nearly as flexible.
Fantastic. So now I know why my car tyres keep getting holes in them. Thank you very much, Dave. Helen, his question for you. This is from Paul Billington. He says he was in Germany at the weekend and noticed that they have a wonderful aquarium in Konstanz, which is where he was. And he says they have huge tanks with various kinds of ray in them. I noticed the painted rays, in particular, repeatedly swim along with their nose out of the water. Is this a known behaviour? Why are they doing it?
Fantastic. I haven't been to that particular aquarium, but it does sound wonderful. Now, it's possible that these stingrays were after food, because they do tend to get fed a lot. They could have been sniffing around for that. But there's also been thoughts that similar creatures to the stingrays, which are the sharks, because they're quite closely related, might possibly have the ability to sniff the air. There was a study in Russia in 1994 about oceanic whitetips, which are quite dangerous sharks, that not very dangerous, but quite dangerous sharks that go through the open ocean. And they were seen to actually sniff above the surface of the water. Similar of thing in great white sharks. And these scientists actually looked at the sensory parts of their snouts, and they think that there is a possibility that they were actually detecting smells in the air, which actually would move much more quickly in air than in the water, because their volatile chemicals will disperse much more quickly. So perhaps they were doing better than their competitors at smelling things like dead whale carcasses that wouldn't be so smelly underwater. It's possible that might have been it could have been that they were smelling.
Hopefully no dead whale carcasses in the tanks in the aquarium.
I hope not, no.
Sounds lovely. A quick question for you, Chris. Paul has asked us why do they use carbon dioxide in fizzy drinks? Could you use something like nitrogen instead?
There are a number of reasons for this. One of them is that carbon dioxide dissolves really quite well compared with nitrogen. Nitrogen will not dissolve. It's very, very insoluble. You have to work quite hard to make nitrogen dissolve, and that's why when you get the bends after you surface too quickly from diving, it's the nitrogen that bubbles out of your blood and forms bubbles that causes the bends, because it just doesn't want to dissolve. Carbon dioxide does. The other thing that carbon dioxide does do when it goes into water, and one of the reasons it dissolves quite well, is because it reacts with water to make carbonic acid. So CO2 plus H2O goes to H2CO3, that's carbonic acid, and this then dissociates, breaks up into H+, that's the acid bit, the hydrogen ions, plus HCO3 minus bicarbonate. And when you have H+ ions, acid in a liquid, acids taste lemony. So you get this very nice lemony flavour added to the drink. So the carbon dioxide not only dissolves well, so you can make your drinks really fizzy, you can get lots of gas in. It also means that it tastes nicer, and you can get lots of gas dissolving, so it then comes out gently in the drink, so it stays fizzier for longer. So I think there's a number of reasons why CO2 is a good choice, and also it's free. You can get it from the brewing industry, yeast produces it, and you don't have to even purify it. You can just get it off of the yeast and you've got it, so that's why.
Cool.
Right, well, next week we're going to be finding out about the science of mosquitoes and why some people are mosquito targets, like my wife, and why others, like me, just get ignored. Well, it's all down to chemicals that come out of our skin, and some people have their own built-in mosquito repellent, while other people act as a perfect mosquito trap. And we'll be finding out from the people who are doing all this research how it works and how we can use it. Thank you very much for listening, and we'll be back at the same time next week. Goodbye.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.